evaluating our world because a lot of the work that Luke does on forests and soils and ecosystems that intersects with some of the work that our lab does as well. Luke currently is a research associate professor at Michigan Tech up in Colton. We were just discussing taking a long drive, but thank you for making it down for today. And he is also, since 2010, has been at the Northern Institute of Applied Climate Sciences, which is a research institute in Colton, Michigan, and part of the U.S. Forest Service. He got his bachelor's degree in Wittenberg College of Biology, and then did his PhD with Peter Curtis at Ohio State. Was a postdoc at Ohio State, and then for a bit at the University of Michigan Biological Station, where he got heavily involved with getting all of the soil carbon people organizing together as part of this international soil carbon network work. More lately, Luke and I have been chatting a bunch with folks at the National Ecological Observatory, trying to get more work together with the folks who are working in the Great Lakes, which has been exciting and fun to think about how we can be better collaborators across all of the ways that we think about Midwestern forests and abundant ecosystems. So today we're going to hear a little bit about that work, particularly about forests and forest carbon and the impacts of climate change, and I'll turn it over to you.
Thank you, Ankur, and thank you for being here in person and virtually. This is what I'm going to try to do, is offer you a long-term perspective on climate change and forest carbon and how management fits into that. And when I say long-term, I mean looking back to the past and forward to the future. Before I get there, I want to tell you a little about where I really prefer to be hanging out. What I really would like to talk about is soil carbon. As Ankur said, it's an important area of research to me. I think there's really nothing more interesting than soil organic matter, but it's mostly poop and dead bodies on a really tiny scale, and who is interested in that? Also, I work for a climate change institute, and I have to think and I have to stretch and think a little bit about how soil carbon fits into this bigger discussion of the carbon cycle of climate change. So let's get to it. I have heard a lot of conversation, more now than ever, about the role that forests play in climate regulation and the carbon cycle. And that leads me to offer you this quote from Mark Twain, by way of Bert Barnes, forest ecologist, who applied this to the topic of plant communities and plant succession. There's a lot of conversation about forest carbon, climate change, and I don't think that it's leading to the most fruitful places. So I hope that I can help offer you some new information about forest management, climate change, forest carbon, and at least stimulate some thinking for you, as I have had to do a lot of as I put this talk together. This talk starts by making a reality check. It's almost 50 degrees outside today. It's March. The climate has been changing for a while. I myself don't really like that. I like the climate that I've lived with in my life. I like the climate the way it is now. I don't want the things that are happening with the climate to continue, but it's going to do that. We've seen a lot of warming already. We've got a laundry list of different observed climate changes that you can see today, and projections that dwarf what we have seen so far. What we have seen is nothing yet. So I'm not going to belabor these points. I just want to make the point that as troubling as it is now, climate change has got a lot more to go. And that's the backdrop. When we think about long-term things like forests, forest management, we have to think about those long time scales. I think it's equally important not just to talk about the changes in climate that we have observed thus far, but to talk about and think about the impacts that they have on forests. The national climate assessments and scientific literature give us a lot of facts, a lot of information about how climate change is impacting forests. We can look at those as bulleted lists, as I have shared for you here. We can look at handy flow charts like this that separate things like the environmental changes themselves versus the way that they affect disturbances and how those disturbances affect forests. We can think about slow changes or rapid changes, everything from the press disturbances of climate-induced drought stress on top of insect outbreaks, on top of multi-year drought. Or we can look at rapid changes like an entire forest burning up in one wildfire. We need to think about the ways that these changes are interacting. Climate changes are interacting with other disturbances and stressors that are acting upon forests. And as time goes forward, we are going to see more and more of this happening, more direct effects of climate change on forests, more bad synergies between climate change and other stressors on forests. And the things that we think we know about how those affect forests are from a past that we have observed and are not going to see again. And the faster the changes get, the harder we got to work as scientists just to keep up generating new information that has any predictive value about what to do about it. So another reality check I'll offer is this. As many of us lovers of the earth need to be reminded, forests are not just these static refuges where we go and see beautiful things and escape the stresses of life in the city. Forests are not museums or nature preserves. They are dynamic places, and people have been at the heart of those dynamics for thousands and thousands of years. Like the climate that we have, forests are compromised in a lot of ways. They're compromised ecologically, they're compromised structurally, they're compromised functionally for a variety of reasons that I will go into in the next few slides. And even if we weren't facing a climate crisis, forests would still be facing a whole long list of stressors and threats. There's the direct effect of atmospheric CO2 pollution on forests. There's atmospheric deposition, there's invasive plants, there's pests, there's pathogens, there's a whole lot of challenges facing forests, and climate change just layers on top of those. Well, how did we get to here? I think we start by looking at the past and what has happened leading up to the present. So from a historic perspective, how we got to where we are is, first of all, by long-term Native American management of forests. Humans have managed the forests of North America for at least 8,000 years. The first thing that comes to mind for most of us is fire. But it wasn't just idyllic burning out of the underbrush in dry pine and oak woods for better blueberry picking. There were a lot of different uses of fire by prehistoric Native Americans. There were a lot of uses of fire by Native Americans who were actively managing the landscape when Euro-Americans arrived. This engraving here on the right shows farm country in the 1580s in present-day North Carolina. Native Americans used fires for all manner of things, including eliminating forest cover from certain places, up to and including eliminating forest cover. So management has been going on for a long, long time. More recently, mostly in the 1800s and the early 1900s, native land management was abruptly displaced by a wave of land uses that were usually exploitative and often violent. And after this great cut and burn over, let's not forget about the many decades that followed where people were trying to subsist on this degraded and decimated landscape. The Lake States are really the microcosm for this. A lot of good books on the topic, but they overemphasize, these books, the timber baron ideal. The idea of the wealthy East Coast businessman, the cut out and get out. Yes, that all happened. But there were many decades of people who were left in the wake of this land abuse, cutting the second growth timber or the low value timber, people trying to farm. That is all built into the history of the forest that we have today as well. What we have with forests by and large reflects all of this past history. In the more or less 100 years since this great cut and burn over, we've seen a version of forestry become established that is two things. One, it is way more sustainable and ecological than this. And two, it has really retracted. Over the course of decades, in the latter half of the 20th century, we've seen a general decline in forestry as an economic sector, as an industry. All the attendant kinds of decline have gone along with that. Loss of rural employment, loss of markets for wood materials, loss of skilled technical workforce, loss of scientific capacity. What do we have as a result of these thousands, recently hundreds of years, and then in recent decades? What we have is extensive areas of ecologically degraded forests, and what those really are is very vulnerable to climate change. We have differing values as a society and difficulty communicating about forest management. It has become a pretty contentious issue. The people who do management, the professionals who do that work, they have less social license than ever because people have lost faith in them. And they also have less capacity than ever because they're trying to do more with less than ever. I think that we can admit that we are in a situation with many problems with regards to forests and the climate and the carbon cycle. What are we going to do about that? What do we want this to become? Well, here are a few proposed solutions. The loudest voices in most of the discussions that I'm aware of as a scientist at a climate change institute are these two. One group of people yelling really loud that nature knows best how to take care of itself, and that when we monkey with it, we're more likely to mess things up than improve anything. And that the best thing we can do if we care about forests and the climate is let forests alone so they can store carbon. There is another loud faction that says we should intervene everywhere. We should manage all forests, management, technology. These are things that can provide a tool for every problem. We should increase our economic self-reliance and be more self-sufficient as a country in generating the fiber, the fuel, the forest products that we need. And by the way, younger forests are more rapidly sequester carbon. You know, both of these are elements, both of these arguments have some compelling features. In the first case, you know, it's true. We have a long track record of messing up Earth. So believing that we can do better now, it's arguable. But we are a consumer society. If we are going to continue to depend on forests for all the things they do, but we're not going to invest in them or take effort to manage them, that's an equation that doesn't balance. And even if forests could recover from the burden of all their accumulated problems, we can't just set them aside for a couple hundred years and let things sort themselves out. We need things from forests. As to this second argument, forests are a lot more than fiber and fuel. We need a lot of other things from them, and we need them for their own sake. And although there are a lot of good tools in the management box, you never have to look very far to see management that could have been done with a better eye towards the future. So I think polar opposite philosophies like these two, they don't lead anywhere. They are a disservice to forests. They're a dismissal of our moral obligation to be stewards of the earth. I think that now more than ever, we have to accept uncertainty, we have to acknowledge complexity, and we have to use science to figure out how to do the best we can with what we have. Science is the tool that can inform management, that can tell us what we can do to help forests recover from what they have been through and position them better for what they are headed into. And in particular, managing in the face of uncertainty, accepting that we're not going to know, is something we still have to do. The first thing we can do to help forests, to help ourselves, are to keep forests forests. This is anything but a foregone conclusion in a lot of parts of this country. But the evidence shows that one of the highest impact things we can do in terms of forest carbon is not cut them down and turn them into farm fields or parking lots or subdivisions. This graph right here shows forest cover by New England state on the top and population. And we see a decline in all New England states in forest cover, yes, a great big decline during the Great Cut and Burn Over, and then, of course, the recovery. But look, most states are declining forest cover again. That's the first thing we got to stop if we want forests to help us, continue to help us, because they are anyway, keeping carbon out of the atmosphere and in ecosystems. I want to point out that there's very good work on the carbon balance of the different land uses in the east and northeast and elsewhere, and it shows that an order of magnitude more of the forest carbon sink, the offset that forests provide of our emissions, an order of magnitude more of that comes from just forests remaining forests than from any other kind of land use change. The uptick that we saw over these decades in forest cover as they grew back after that Great Cut and Burn Over, that's a drop in the bucket compared to forests remaining forests. And I also want to say a little bit about other types of land use change. I'm crucifying deforestation for development here, but that's of course not the only kind of deforestation that's happening in the Northeast or the Midwest or anything else. I'm of an age where, growing up in the Midwest, I remember a time when every 40-acre farm field had a fence row about it. Those are gone. You can drive out into the countryside of Dane County and you can see them get bulldozed away. The last one's remaining. You can see a lot of places where, farm fields have for sale signs in them. Farm to development, that's also bad from a forest carbon point of view. Because what do you think that loss of farming acreage does to the way that the farmer farms the rest of that property? That causes the farmer to deforest for agriculture, which is also bad from a forest carbon point of view. There are connections that play out among different types of land use change that mean we cannot separate out just what's happening with forests from what is happening in the wider landscape with patterns of land use change. The second thing we can do to help forests help us with our climate problem, with our atmospheric carbon pollution problem, is silviculture. I've borrowed here a definition from the Society of American Foresters Dictionary of Forestry of silviculture. What I argue here is that as a precursor to any kind of forest management, we need to assess climate vulnerability as a precursor. That should just be the default. Anytime we're talking about any action in a forest, we have to think, what is the climate vulnerability? Well, that is the combination of climate change impacts on that place, on that forest, plus the adaptive capacity that it has. And things like climate impacts and adaptive capacity are things that make the most sense when we talk about them in a hierarchical way. What I mean by that is regional climate change impacts are filtered through the unique conditions of individual places. Think about global climate change, regionalized climate change, site-specific impacts. Adaptive capacity is something that an individual forest has in the context of the landscape where it's embedded. It's things like, all right, we're talking about this 40-acre parcel of forest, but what is its ownership in the context of wider ownership? How is ownership influencing management in that landscape? It's things like fragmentation versus connectivity of that forest to other forests within its landscape. It's also spatial hierarchical relationships with things like how water moves between different landforms on a landscape. There's a lot of reasons to assess climate change vulnerability as a precursor to all forest management. First of all, it aligns our thinking at the outset with the first fundamental goal of silviculture for climate adaptation. And that is, first of all, don't do management that is maladaptive for climate change. There are some kinds of management that are very obviously maladaptive for climate change. One example would be what's often called high grading, cutting out the best form, healthiest sugar maple trees from a northern hardwood stand, and leaving all the beeches with their bark disease and their 3% survival rate, and the poor form, ice-damaged red maples and sugar maples, that is maladaptive. That's not going to make a healthier forest. That's not going to be good for the forest itself. It's not going to provide any climate change adaptation. Other times, what is maladaptive is a more nuanced question. We can say, all right, suppose there's a plan for a public lands project in northern Wisconsin that involves clear-cutting aspen birch forest on a sandy outwash plan. Well, on one hand, that might be maladaptive because we know from the science that aspen birch forests are already under a lot of climate stress. They're near the southern edge of their range. So they're kind of climate change losers, so to speak. Sandy outwash plains are hot, dry places where climate loser species are going to be especially stressed. So doing an action like this would be maladaptive. We would be regenerating an aspen birch forest in a place where it is unlikely to do well under continued climate change. We should do something different, right? Well, on the other hand, if we get a bit deeper into that question and we keep an open mind, I don't think it's necessarily maladaptive to climate change. There are other ways to do aspen birch forestry. Maybe rather than one large clear cut, smaller patch cuts, or integrate areas of reserves, islands of unharvested trees into a larger clear cut matrix. There's a technique called aspen shelter wood, where you leave strips of aspens or groves of aspens in ways that provide shading and inhibit the rapid regrowth of aspen that result in bigger trees faster after that forestry has happened. That same practice can result in a more complex spatial structure. That's one aspect of adaptive capacity. Complexity is something we generally view as good for adaptive capacity. That can be structural complexity, that can be species diversity, and so on. I just want to point out that when we talk about adaptive capacity, it is familiar things that make a lot of sense, like having a diverse assemblage of species in a forest, and having the resulting complex, spatially variable structure that often attends having a diverse mix of species. But there are other elements of adaptive capacity that collectively we don't talk or think enough about, but are important for how they connect to climate change. And some of those include things like functional diversity. It means having assemblages of species that have different rooting depths and water use strategies. You know, a lot of what we're seeing with climate change is too much water, not enough water. Maybe we need to have species that are, you know, able to capitalize on those very different conditions and that increased hydroclimatic variability. Adaptive capacity can also be things like disturbance recovery pathways. What happens when you have a windstorm blow down a few trees or an entire stand depends upon what is growing there waiting in the wings to come up after. It depends upon what species are there, how high are they, what strata of the forest are they in. There are a variety of different kinds of adaptive capacity. And that's the thing that we need to be thinking in management of increasing for forests so that they have what they need to buffer the impacts of climate change. And the third goal of silviculture for climate adaptation gets back to the controlling and health parts of this definition up at the top. I have tried to make the point that there's a lot of forests that are not healthy and are not on a good climate adaptive trajectory. And silviculture is the toolbox where we can redirect these conditions in a more desirable way, a way that increases the adaptive capacity of forests. And the point I want to make about this is that kind of intervention, when you have a forest that is, you know, homogeneous in its composition, or has a lot of poor form trees because of decades and decades of high grading, these are kinds of forestry that do not do well on their own. They cannot happen if there is not an effective and self-sustaining forestry industry in the area. So we can't help the vulnerable if we don't also have forestry that's happening for the economic reasons that it has to happen in the same landscapes. I think it's important to ask how we could know that we're having any success, any impact, if we can do these things, if we can get to where there's more management being done with climate adaptation in mind. What are some of the things we might see that tell us it's working? Well, we can look to ecological metrics, like things I mentioned, compositional diversity, stand structural complexity, landscape age class mosaics. If we have a lot of different ages of forests on a landscape versus a landscape that's dominated by one age class, that's structurally homogeneous. These are ecological things we could observe and measure that say we're doing better. We could see social outcomes. We might see that climate adaptation just continues to become more mainstream than the DNRs and the Forest Service and all the different entities, government and otherwise, that manage forests. We could hope to see better scientific literacy among the people doing the management and among those of us in the public who provide input on that management. Better literacy on forests and climate adaptation and forest carbon and how it works. And we could benefit from an improved bioeconomy. We live in a world where it's getting increasingly hard to find good forestry advice. There's a lot of people who own a lot of forests that are going to do something with those. They might sell it to developers, they might cut some timber out of it, they might harvest it for firewood. There's a whole range of options that the wide world of ownership has for forests. And it's getting harder all the time for people in that situation to find good, scientifically informed advice about forest management. We could have that information much easier to find if more of that information was flowing through a climate adaptation lens. As I've also mentioned, a bioeconomy has everything to do with the economic opportunities for people in rural areas, people who vote. It has everything to do with the economics of what kinds of forestry are possible. If there's no market for there is no market for low-value products of the kind that are generated by forest improvement management, if there's not also forestry happening for other reasons. Here's where I want to pause and reiterate a few points because they're the basis for the next part of my talk. First of all, we got to keep forests forest because that's the first thing that has many climate adaptation and carbon benefits. We have to think about forest management, climate vulnerability, adaptive capacity, and carbon all holistically. They're all connected, and we have to think over many decades. It's not over the right now, it's where do we want these places to be in 50 or 100 years or more. And the last thing I want to stress is that how management affects forest carbon depends upon what you're starting with. It depends on what that forest has been through in the last 20 years, in the last 200, in the last 2,000. It matters where that forest sits within its landscape context, its connectivity to other forests, its connections, hydrological, and so on. And now is where I turn the corner to a more familiar place and start showing you graphs with Honeyprint. This is a more familiar kind of talk for me, and I hope it's equally convincing. Recognizing that there are different places and different situations, forests present us with different situations when we're thinking about climate change and carbon management. This part of the presentation is going to be case studies primarily. And in the East, most of the ecological studies of forest carbon, they frame this topic of research in the context of long-term carbon recovery after that regional exploitative disturbance, the Great Cut and Burn Over. The result we see in this ecological literature is projections of the forest carbon sink that look like this. We had a period where the primeval forest was cut down, burned up, and farmed over, and now like a fairy tale, it's growing back, and that's what it's going to do. It's just going to, if we leave it alone, it's going to reach some high point of carbon storage and just stay the same. That has been a useful way to do research about regional forest recovery after large-scale disturbance. But there is a big problem with that way of looking at the problem. To use a term that I've heard more of lately, we need to decolonize this way of looking at things. This was not a primeval forest that we wandered into and had our way with. This was a managed landscape. For millennia before Euro-Americans arrived, these forests were managed. They were, in some cases, deforested. Second of all, the ways that we approach studying this kind of a long-term phenomenon are usually by going out and measuring forests that are 5 or 50 or 100 years old and plotting those points on a graph like this. It's called a chronosequence. We assemble this view of what happens as forests age towards maturity by measuring them at the whole range of different ages. You know, chronosequences are great tools, but what they are is hindward looking. They're looking at things that happened in the past to different places. And they're assuming that that's the only thing that differs, is when that thing happened, like when the clear cut occurred. If we take a chronosequence like this and say, all right, we got a 100-year-old forest, if we leave it alone for 100 years, what are we going to have for carbon? We're fooling ourselves if we think that is going to transfer to 100 years in the future. I want to get to the point where I can share with you some benefits of the chronosequence approach, because it is a very important kind of research. It's one that I use. The best way I can think to do that is to show you some examples. And this slide shows an example from the University of Michigan Biological Station over across the pond, tip of the mitt. This is as good a chronosequence as you can find anywhere. We have a landscape with a remarkably consistent degree of similarity in things like soil, microclimate, landform, things like that. And here, all in a cluster, we have these stands that were clear-cut and burned at different times. And almost everything we can control, soils, microclimate, forest composition, it's all the same because they're next to each other. So we can do this kind of a chronosequence. We can look at stands at different ages and how is their net carbon sequestration, or NEP, or net ecosystem production. This figure is one from a paper by my colleague Chris Goff. It's from a 2007 paper. What he and his co-authors found at that time, or posed at that time, I should say, was that after stand replacing disturbance, so here we are, mature forest, we went down to 0. The forest was no longer a net carbon sink. It rapidly came back, but when you do a second harvest and fire, like these burn plots, everybody got cut and burned, you know? But then these stands got cut and burned a second time. And we're talking about what happens when you do subsequent management of forests that have this common regional land use history. That second disturbance knocks down that ability of the forest to sequester carbon. It reduces the NEP. Well, Chris and I and Newt Nadelhofer, our colleague, have had funding now for some years to study these stands right here, burn plots, as well as some old reference forests on the U of M biostation landscape, and look at these trajectories of carbon stocks, carbon sequestration rates, in comparison to this perhaps potential value that the old stands represent. And my next few slides are going to show you some of the findings of that research. First of all, some results from Cameron Clay's master's paper. Perhaps not surprisingly, one of the things we see is that after a stand replacing disturbance, as the forest ages, biomass accumulates. Total ecosystem carbon follows the same trajectory. Soils are not particularly responsive in this type of ecosystem. So we can expect, where there is management of forests, up to and including clear cutting and burning, that forest carbon will come back over many decades. The old reference stands right here 2 pines and one sort of a northern hardwoods hemlock stand, they showed there's the potential for continued carbon accumulation for well over a century, maybe several centuries. One important finding here was that with the exception of this oldest stand, down here we're looking at total ecosystem carbon. We do carbon budgets looking at the annual inputs and outputs of carbon to all of these different standards. That's net ecosystem production, carbon in, carbon out, the net balance. With the exception of this one, we can't actually say whether these are carbon sinks or sources. Only that one site is definitely a carbon sink. Part of the reason for that inability to say with confidence what we know to be true or think to be true from our flux towers is because of variability in our methods. I'm going to tell you a little bit about that. But first, I'm going to tell you something else. This one, that is the strong carbon sink, it has by far the most intensive management history. A tribal elder of the Burnt Lake Band who has long walked on, Bernie Parkey, once said to me, "You tree huggers think that's a nature preserve. I call it Indian farm country." It was managed agriculturally for hundreds, if not thousands of years. It is today the biggest carbon sink. It's also the place that's on by far the best soils and the best landforms, so it's not entirely representative of what we can expect from these chronosequence stands on their sandy soils. That's the aside. I wanted to talk a little bit about variability, because that reminded me of another paper.
Sorry, could I just ask one quick question?
Questions at the end, please.
Okay.
There's a paper that I read as a graduate student that really was one of the earliest to inform my thinking about this question of net carbon balance of old forests versus younger managed forests. And the figure that is the most about that in this paper, which has basically been validated once again in a paper published just last year from the same sites, is that Willow Creek, the site with the more active management history, is a much stronger carbon sink than the old growth forest, Sylvania. That's a pretty reliable pattern out there in the world, and I will talk more about that. But this was all about variability. There are 2 different years presented here. When I look at this graph and see the degree of interannual variability in net ecosystem exchange, which is the tower-based version of net ecosystem production. Negative means carbon towards the earth, positive means carbon in the atmosphere. I see what to me is a pretty surprising amount of interannual variability. But one of the findings of this paper, at least that I took away, was that interannual variability is actually smaller than the variability associated with methods, with how you screen and handle missing data, problem data. Flux towers are a really, really important part of the puzzle when we're assessing carbon stocks, carbon sequestration rates. It's a really rare thing to have this kind of a design like Conquer and collaborators have with looking at managed and unmanaged forests and wetlands and lakes all in one landscape. Flux towers are really important, but like any technique, methods really matter. And methods variability is real, and it does hinder our ability to make strong statements sometimes about the carbon sink strengths of different ecosystems. That takes me back to UW-Madison, where I want to say a few things about variability. Data we've collected over the last 20 years show how the climate has changed in that time scale. 20 years ago, when collecting soil respiration measurements, soil respiration being the largest carbon loss term from the ecosystem. I was looking at whether autotrophic or okay. Soil respiration is a very large carbon loss term from any forest ecosystem, and it is temperature sensitive. And in the last 7 years of our measurements, we see soil temperatures hanging out in this zone where they never used to happen. And soil CO2 emissions are non-linearly positively related to soil temperature. So when we see a little bit more of the time with soils at this kind of a soil temperature, we're getting a lot more soil respiratory CO2 emissions. that's one example of how variability in the methods we use to do things like assess carbon balance depends the answer we get. We think from our flux towers that these forests have always been carbon sinks for the last 21 odd years we've been measuring them. But we think from some of our other methods, we can't really say whether they're carbon sinks or sources. The picture is probably worth more. This is the 2017 burn. I don't think that was on the map I showed you. The most recent experimental treatment was a cut and burn in 2017. All of the trees you see here, these were things that the logging operators didn't bother with. They're too small to cut. So these are not trees that have grown back in 5 years. This is a picture from 2020. One of the audience is in this picture. This area still looks the same. 6 years on, there are no aspen suckering up from the roots. There's very little stump sprouting. This is what a forester would call regeneration failure. That's not something that anybody really thinks about or has been prepared to think about in northern lower Michigan. This doesn't happen. But it's so hot and so dry out there in the summer right now that things are starting to look different. This is the climate of the future we have to look forward to. We have to think about how to modify forestry, or in some places to do forestry, to ensure that this doesn't happen if we want to keep forests as forests. So I've said a few things about chronosequences. I hope that I've given you some idea of the kinds of things they can tell us about long-term trajectories of carbon accumulation after a disturbance. But I also hope I've convinced you that this ideal of a primeval forest magically recovering from a disturbance is maybe not the best way and certainly not the only way to look at forest landscapes and what they're doing with carbon. Well, what's another way we can look at forest landscapes aside from these trajectories, these chronosequences? Don't look at this and get overwhelmed, these box plots. Look at this. Landscape mosaics. That's what exists out there in the forested world. Landscape mosaics of different ownerships of forests, different management histories, and current management regimes. Landscape mosaics of cover types. Out there in the world, this is what exists as landscape mosaics. And what I offered this for is to show an example to you. This you can think of as the net carbon accumulation of different management treatments over a 100-year time scale. This is from work done in Maine by Josh Kulik and others. We have an unmanaged condition here that over the course of a century, based on measurements and models, sequesters about a megagram of carbon per hectare per year. We have some types of forestry that sequester a lot less carbon per area per time over that century. We have some that actually sequester more carbon. Some management regimes that sequester more carbon than no management. This is what exists out there in the world. Stands managed differently because of ownership, because of transitions of ownership. You know, when the parents die and the kids get control, like this is happening. These are things that matter to how forest carbon works at landscape and regional scales. Another example, I'm not going to go over a point here. I just want to point out we're looking at carbon metrics and biological complexity metrics. These are for red pine and trembling aspen stands in northern Minnesota. I want to point out a couple things here. First of all, different shapes of curves. Pine, this complexity metric, evenness of species in the stand, slow linear increase. Aspen, off to a big start and plateaus. Different stands have different rates of how biological complexity develops after they're managed. Cover type matters. Mosaics, landscape mosaics of cover type explain a lot of what we get in terms of forest complexity and forest carbon. The most important thing that I hope you'll take away from this talk are these 4 panels. showing total ecosystem carbon for the pine, or the aspen, and annual carbon sequestration. Yes, if we leave forests alone, they continue to sequester carbon, but at an ever slower rate. This is a nearly universal pattern out there in the world that seems to be getting forgotten a lot. There is an undeniable trade-off in almost all situations between carbon standing in the ecosystem and how fast that forest is pulling it out of the atmosphere. So that brings me to the idea of trade-offs. Most management, for a whole range of reasons, is multi-objective. It's easy to point the finger when we see bad management and say, oh, that was just all about profit right there. But far and away, the majority of management, especially on public lands, is about a whole lot of different objectives. And the people doing that are trying to balance all those objectives in one landscape. As a result of there being a lot of objectives, there are a lot of different forest conditions at landscape levels. Carbon is kind of the latest of the management objectives. It is a very good thing how much attention people in management and in the public are now paying to forest carbon management, because forests are a really important part of our climate problem, and their ability to store and sequester carbon is an important part. But we have to accept that carbon can either work in tandem with some of the other objectives, or it can be at odds with some of those. And I just included one snapshot of a paper here because I think some of the best work being done on this idea of carbon trade-offs is work done by Caitlin Littlefield and Tony D'Amato and others, looking at how in some cases, for instance, you can have very good synergies with carbon management and wildlife. Early successional forest habitat and rapid forest carbon sequestration go hand in hand. Those are very different goals than large standing forest carbon stocks and habitat for organisms that need structurally complex or old growth-like forests. But if we have our eyes wide open to these trade-offs, and we agree that all of these things have value on some part of a landscape, that gets us thinking about how to balance these kinds of trade-offs. I want to say a little bit about the West, because that's where climate change and carbon and climate adaptation is, it looks very, very much on top of us right now. There's a lot of overstocked forest in the West because of a combination of not enough management and too much management in the past. Most of these forests have the potential to continue sequestering carbon for centuries, because these are very long-lived tree species. These can remain carbon sinks for a long time. On the other hand, as time goes on, the odds of any given forest going to the atmosphere in this year's fire become larger and larger. So what do we have here? Are trees stored carbon, or are they fuel waiting for the next fire? I think if we reduce this down to a binary, we would say that it has to be one or both. But if we use climate adaptation to think about this, we would start to look at landscapes and say, oh, you know, topographically protected places, river valleys, northeast slopes, places that aren't going to burn as severely or are less likely to burn, those are good places to leave forests alone and let them increase standing carbon along with all the things that go with it. Places that are fire vulnerable, places that are easy to access, those are places where maybe from a climate adaptation point of view, the best thing we can do is diversify the landscape by managing those more actively for their rapid carbon sequestration. Another thing I want to talk about a little bit is disturbance legacy carbon. Pet topic. It was recently brought up for me, and I hadn't thought enough about it, but I don't think anybody is. These are pictures of century-old woody debris from the U of M biostation. Here's Chris Goff next to a stump that was 300 years old when it was cut down 120 years ago, and it's still out there. This is a coarse root in a soil pit being dug by Brady Hardiman. It's about as big around as my thumb, and it's still there. just 20 centimeters down in the soil, there is still legacy carbon. We are really bad at capturing how much of that is out there because it's spatially variable, and a lot of our sampling techniques as soil scientists are specifically designed to avoid features like that. But it's a lot of carbon. And because of where it is down in the soil, it's in a place that is probably very protected and likely to last centuries longer because of that thermal modification, because it was burned, because it's being charred, that slows down decomposition, and the fact that it's buried. That's not the only anecdote. Anybody who's worked in soil has seen things like this. Now, another thing is this type of feature is really important to other things we want forests to do, even when they have been burned up in a terrible wildfire. The engineering people know a lot about the role of roots in anchoring slopes and what density of residual roots you need after a wildfire to keep the whole mountainside from coming down into town with the next big rainstorm. Let's apply the same thinking to think about how long that carbon lasts, what is its fate in soil, how long does it persist, how much is there, what is the role of that in the carbon balance of this forest management question. When we cut down a forest, take some of that carbon out and build a house with it and leave some of it in the woods and the soil, we have to account for that too in terms of what the atmosphere sees. Okay, now here's where I finally get to talk about what I like to study best, soil carbon, the largest carbon pool of all. Almost all of the discussion you will hear anywhere you go and listen about forest carbon management is above ground, but most of the carbon is below the ground. So to me, that's a problem. My colleagues and I work to pull together data sets from published studies of these points, use meta-analysis to look at things like what was the amount of soil carbon before the harvest happened, and what was the amount of soil carbon after the harvest happened. Then we also use data from the blue points and the red points. These are soil survey paddons and national forest inventory plots. We use 3 different data sources and one ecoregion at a time. This is the lake states. We work to answer the question, how does management affect the largest carbon pool, soils? The lake states are, of course, nearest and dearest to my heart. They're also the place that has generated the most convincing story thus far. When you have 3 different data sources, you can do things like say, do you see the same results across the 3 data sources? And I couldn't believe it when I looked at harvest effects on topsoil, that's the A horizon, topsoil carbon across these 3 data sets. 17 to 20% decline in topsoil carbon with forest harvesting in the lake states. I have hardly ever seen such a convincing pattern in doing this kind of work. But what I'm not telling you about is what's underneath this result. Not every place responds the same way. There are some places that gain soil carbon with harvesting. There are some places that lose soil carbon with harvesting. That has to do with the soil texture and the soil parent material. Those are 2 things we can map quite well at scales like this. And then we can do things like create maps that we give to our Forest Service or other partners who want to know this kind of information so they can plan management that is more carbon positive. We also produce things and work like this, like what we call a tactics table. All right, if you know you're in a place that is going to be probably a carbon loser, a soil carbon loser when harvest, what are some things you can do that have support in the literature to protect that soil? This is the kind of tool we make from this sort of research to enable people to make carbon-informed management decisions. I can offer you 2 more slides that make this real, that make this place-based. Again, member of our audience in the picture here. We found that outwash plains were places likely to lose soil carbon in the lake states. If you know about outwash plains, you're probably not surprised because they are often very low productivity, they're droughty, they have an extreme climate as a result of where they sit on the landscape. They're like the deserts of the lake states. So in some ways, not surprising that they're prone to losing soil carbon. So we can come up with some suggestions about things to do to protect outwash soils during harvesting and prevent carbon emissions from those soils to the atmosphere. And the last place that I'll provide as an example, the other end of the spectrum, we found that post-glacial lake plains, these are places that are likely to show soil carbon gains when forests are harvested on them. But these are also places that are kind of difficult to operate in. They're usually very wet, because once upon a time they were ponded lake plains. They have fine textured soils, or they're organic wetland soils. These are places where it's very difficult to do good forestry without damaging the soil. So those are reasons why maybe we might want to give them a wider berth. Where you have wet spots, soils that are prone to carbon gains with harvesting, you might be more likely to damage them physically by doing forestry than you would be likely to gain carbon from forestry. So we can think about multiple objectives again. We can think about lake plains or isolated wetlands as places where, for example, we leave bigger buffers. Here's a figure from a review paper by Katie Hoffmeister and others on seasonal ponds and forest management around seasonal ponds. It shows that no matter what kind of parameter you're measuring, whether it's the veg or the amphibian community or the biogeochemistry, you have a lot of initial disruption to ecosystem functions after management. It comes back, but a lot of things take decades. So these are places where when you decide to increase the buffer size around this kind of feature, you might be fulfilling several objectives. You might be protecting the soil from structural damage. You're also increasing the size of the residual carbon left on the landscape. You're increasing the reserve carbon held there by leaving a larger buffer. And this is one of the ways that I'm offering to you to think about specific places and how when we look at them for what they are and what they have and what they've been through, we might arrive at a different set of conclusions about whether and how to do management in them. My closing thoughts are here. There is no one answer for every place, whether we're talking forest management or climate adaptation or carbon management. We have to filter through a hierarchical perspective. We have to think about regional climate change, site level vulnerability to that change, adaptive capacity of that place. All of these things come together in a holistic perspective. If we just look at forests as carbon, and carbon as the solution to our climate problem, we're not going to get anywhere. If we do or don't take an action in one place, it's going to cause a reaction elsewhere. So if we're going to decide we want to harvest forests less and keep more carbon in the woods, that's going to make harvesting happen more somewhere else, because we still need all that stuff from somewhere. If we harvest in a place and it reduces adaptive capacity, how is that going to strain forests in other places? Connections. We are people who think about the ways that things are connected, and it's so much more than ecosystems. All of these things are connected. And if we take a narrow view, if we adhere to personal beliefs or philosophies about forest management, about the role of forest carbon in our climate problem, we're going to keep ending up at the same self-reinforcing problem. We're not going to get anywhere. If we accept uncertainty, if we acknowledge complexity, if we use the science of climate adaptation to help guide us, we might get somewhere. We might learn how to compromise on forest management, and that would be to everybody's good. So that's what I have. I hope I've been at least entertaining, if not educational.
Thank you.
Yeah, thank you. It was a really great talk. I was wondering, do you ever take into account like the end product of the harvested material in your carbon budgets? Because some are very long-lived and others are very short-lived products.
Thank you for asking that. Yeah, the fate of harvested wood products is really important. And of course, I don't do that kind of research. Here at Madison is a great place if you're interested in that, because there's the Forest Products Lab of the Forest Service that does that kind of research. And one of the problems with the narrow view of forest carbon that many people have in many ways is that we see carbon leaving the forest and often assume that, oh, it's gone from the forest, that means it's in the atmosphere. Well, if it's junk mail, it's probably in the atmosphere within a few years. But if it's wood going to build a house to solve the housing crisis, that's a very different fate. For what it's worth, that graph I showed from Maine, that did incorporate harvested wood products. So when you account for those, they are removed from the ecosystem, but all those different fates collectively add up to an increased carbon sink, especially when those harvested wood products are used to displace fossil energy. So most sawmills, for example, they burn waste wood to generate electricity that they use in their process. And as a result, they're not burning natural gas, fossil carbon, and sending that to the industry.
Time for one more question.
It seems like a lot of this would benefit from some kind of a risk assessment strategy that would help identify the most vulnerable forests that require the most urgent kind of intervention. Is anything like that going on either at a national or state level?
Well, that's a great idea and a great point. I think that many entities have many different systems of prioritizing where to manage as a result of that risk. Probably a common theme in them is that they're too reactive and probably not proactive enough. Not being an agency employee of any kind, I don't have intimate knowledge of it, but what I think of is, like the fuel and fire crisis in the western forest. I think they're farther along out there in thinking about where the need is most urgently applied to reducing forest fuel densities to prevent those almost unavoidable carbon emissions to the atmosphere. Some of those assessments lead to obvious conclusions like, oh, the wildland-urban interface is a really logical place to focus efforts. Unfortunately, the Forest Service being the agency I know best, I'm also aware that those are often the places where people are most vociferously opposed to management because it aesthetically damages the forest for what they are. So in many cases, the people who need the help the most to prevent their cities from being burned up are the ones who want it the least.
Thank you for sharing a lot of your deep thoughts, and be sure to reach out if you have questions again on forest management carbon. This is your expert here. So let's give a hand again to